Welcome to the deep dive. Today, we're immersing ourselves in the world of high-stakes, high-precision fabrication. I mean, if you've ever watched metal tube or pipe being bent, you know that instant frustrating failure.
Oh, absolutely. The material just, it wrinkles, it collapses.
Or the bend simply isn't repeatable enough for any kind of certified quality work. This is especially true when you're dealing with really demanding materials like stainless steel or even titanium.
It's a constant battle.
Mhm.
You're fighting to get this perfect curve, but the material itself just wants to buckle under the pressure.
Yeah.
Your traditional methods, they're often about brute force, and that just leads to deformation.
Which is just not acceptable for serious fabrication. We're talking aerospace architectural work.
Not at all.
Absolutely. So our mission today is to cut through the jargon and the tech specs to really understand how one specific piece of machinery, the Ercolina Erco Bender Mandrel Bending System, fundamentally changes this whole process. We're going to focus on the EB76 CNC 6V5 and the EB65 models to unpack how this technology really elevates tube and pipe bending from a sort of variable mechanical cast into a standardized high-precision CNC operation.
And we have to look at this through the lens of profitability. The sources make a really clear promise here. They say, by reliably and accurately producing these mandrel quality bends, the user increases profit.
How? By minimizing waste?
By minimizing waste, reducing labor, and just delivering a superior product finish. We're looking at a system that removes that whole mechanical struggle. It's a true shortcut to high-quality results.
Okay, but before we go any further, we have to address the key feature right there in the name, mandrel bending system. For anyone listening who isn't on the shop floor every day, why is the mandrel so critical? Why does it prevent those wrinkles we talked about?
That's the entire game. A mandrel is essentially a specialized internal support. It could be a rod or a ball system that you insert into the tube before you bend it.
So it's inside the pipe?
It's inside. And as the tube curves, the mandrel provides this continuous internal resistance right at the point of the bend. Without it, the outer wall stretches thin and the inner wall just compresses and wrinkles.
Like trying to bend a drinking straw too sharply.
Exactly like that. The mandrel holds the tube's shape, its integrity, ensuring you maintain that original cross-section and get that smooth, clean bend.
So now that we know the mandrel is the key to quality, let's look at the sheer muscle required to push these things through material like titanium. What materials and capacities are we talking about with these Ercolina machines?
Well, they're built to handle the heavy hitters. You're talking about getting quality, repeatable bends in steel, stainless, aluminum,
Titanium, you said.
titanium, and even brass. The capacity is genuinely robust.
Let's break down the capacity of the larger EB76 model because these numbers tell you exactly what kind of structural work this machine is designed for.
Indeed. For a mild steel tube, it'll manage up to 3 inches with a .083 wall thickness. But then you step up to stainless steel, which is significantly harder to work with because of its tensile strength.
Right.
The machine still handles 3 inches, but at a slightly thinner .065 wall. It also does 2-inch square tube. But maybe the most crucial spec for structural fabricators is the pipe capacity.
Which is?
It handles 2-inch Schedule 40 pipe.
Now, for those of us who haven't spent a lot of time around structural drawings, what exactly does Schedule 40 tell us about that pipe?
Schedule 40 is, it's essentially the standard for thick-walled, heavy-duty structural pipe. It signifies a really significant wall thickness and pressure rating.
So bending that kind of thickness,
Yeah.
that takes some serious force.
Enormous sustained force, which is why we're talking about industrial-grade equipment here.
And speaking of industrial grade, the power requirements are a hint that this isn't something you just plug into a standard outlet. We noted it needs 3-phase 480V. What does that signal to a potential buyer?
It signals a couple of things. First, it's a massive power draw. You need that to maintain the hydraulic pressure for bending those thick, tough materials.
And second,
it means this is a serious, dedicated piece of shop infrastructure. It's a tool designed for continuous, high-volume production, not a hobbyist item.
so the strength is there. But what about the precision? What kind of tolerances are we aiming for?
Precision is defined by a couple of key specs. Both models, they boast a maximum bending angle of 185 degrees.
So just past a complete U-turn.
Right. But crucially, the precision of the bend angle is maintained at a razor-thin tolerance of plus or minus half a degree.
Wow, 0.5 degrees.
Yeah. To put that in perspective, that's about the thickness of a few sheets of paper over the whole arc of the bend. That's how repeatable your angles have to be to prevent costly fit-up problems later on.
Okay, let's unpack this then. Strength is one thing, but how does this machine achieve that? That near-perfect, repeatable, plus or minus half a degree precision when working with materials that are inherently variable?
This is where the engineering sophistication comes into play.
We need to look at the CNC intelligence, specifically that three-axis control system.
Exactly. It's captured by the industry term, YBC. Those three letters describe the three critical movements the machine has to control at the same time to create any complex 3D shape.
Like an exhaust manifold for a high-performance car.
Perfect example.
So walk us through it. What do Y, B, and C actually control on the Erco-bender?
Okay, so Y is the feeding axis. Think of this as the linear distance the tube is pushed or pulled into the machine between the bends.
Got it, the forward and back.
Right. B is the rotation axis. This is what spins the tube to set the orientation for the next bend. If you're making a helix, B is constantly moving.
And C.
And C is the bending axis, the actual force applied to the material to create the curve.
So Y and B dictate where the bend happens in 3D space, and C dictates the degree of the bend. But what's fascinating here is the technology used for each. It says Y and B use electric servos, but C uses hydraulic CNC. Why the mix?
It's the perfect division of labor. Electric servos are all about speed, minute control, and incredible positional accuracy. They're fantastic at measuring and moving the tube, the Y and B axis, precisely where they need to be.
So they're the brains, the micro adjustments.
They handle the brains, exactly. But the C axis, the bending, that's where the brute force resides.
And that's the hydraulic system.
That's where you need the hydraulic CNC. Hydraulics deliver massive, consistent power to overcome the yield strength of that 2-inch Schedule 40 pipe we talked about. The CNC component makes sure that this hydraulic power isn't just forceful, but it's applied intelligently, holding that tolerance.
So it's a dance.
It's a perfect synchronized dance between the positional precision of the electric servos and the massive controlled power of the hydraulic C-axis.
And the physical design has to accommodate all these complex movements, right? Especially if you're making tight bends close together.
That's why the machine has an extended bending head. That extension is crucial because it lets the operator manipulate and bend complex shapes without the tooling itself running into a bend you just made. Plus, the programmable carriage lets you get those extremely tight radii that modern designs demand.
Okay, so now we shift from the hardware's muscle to the software's brains. No matter how precise the servos are, the operator has to tell the machine what to do. How does the human element interact with and, optimize this powerful hardware?
The primary control is through an interactive 10-inch color touchscreen. This is the central hub for the operator. It offers auto and manual modes, system diagnostics, all that. But the real optimization, it lies in how the software manages the inherent messy physics of metalworking.
And that messy physics, that ultimate challenge for any fabricator is material memory, or springback.
Exactly. Springback is that tiny, frustrating percentage of a bend angle that a material recovers once the bending force is released.
Right.
Steel springs back a little, but highly elastic materials like certain stainless alloys or titanium can spring back a lot more. You aim for 90 degrees, you might end up with 88.
So if springback is the problem, how does the Ercolina software solve it programmatically? You're not just forcing the operator to guess and check, are you?
No, and this is the game changer. The machine allows for programmable material springback settings for each individual bend angle within a single program.
For each bend, not just for the whole part.
For each bend. If you have 5 bends in one part, all with different radii, different angles, the machine calculates the required overbend needed for each one based on your program setting.
So you tell it the material, it knows the tooling.
And it handles the correction automatically. You program the result you want, and the machine figures out the action required to get there.
That is truly sophisticated. It must remove hours of test bending and scrap material.
Huge savings.
What other software optimizations are there for ensuring quality?
Another critical feature is the programmable auto mandrel positioning. We already established the mandrel prevents wrinkling. Well, the operator can program the exact timing of the mandrel's retraction.
Pulling it out at just the right moment.
Exactly. Pulling it out just enough to release the material, but not so far that the tube collapses once the pressure is gone. Optimizing this is paramount for a perfect interior bend. Also, for safety, there's the programmable tailstock interference zone.
And what does that do?
It monitors the position of the material carriage and automatically prevents costly workhead collisions. A real machine saver.
Okay, let's talk about how an engineer's design gets translated into the machine's movements. You mentioned the machine accepts both YBC and XYZ input values. Why are both of those necessary?
This really speaks to the flexibility of the shop floor. YBC is machine language, where to feed, Y, where to rotate B, and how much to curve C. That's great for fine-tuning.
Okay.
However, engineers design parts using XYZ coordinates. Those are standard Cartesian coordinates that come directly from a blueprint.
So this system accepts both.
It accepts both. A skilled operator can either program by the machine's axis, the YBC, or they can directly input coordinates from an engineering drawing using XYZ.
And for maximum efficiency, especially on complex projects, I assume you want to bypass manual input entirely.
Exactly. The system uses USB for unlimited program memory storage. But the major time savings kick in with the optional file importation. You can take IGES and DXF files.
And those are crucial because...
They're crucial because they carry precise 3D geometry data, the exact shape of the intended part, directly from compatible CAD programs. So instead of manually inputting hundreds of points, the machine reads the engineering file, uses the included graphic bend simulation software to test the path virtually, and it's ready to run.
So an engineer designs a complex pipe structure, exports the file, and that file is the machine's program. That's a giant leap in workflow efficiency.
It's huge.
Here's where it gets really interesting for me. We've spent time admiring the precision, but what is the real-world economic benefit? What does this technology allow a business to do that they couldn't do profitably before?
Well, the core economic benefit is simple. You're eliminating waste and reducing highly skilled, time-consuming labor. If you're forced to make a complicated shape out of multiple small sections, you're just adding substantial cost.
So what are the specific costs we're eliminating by achieving a single seamless bend?
You eliminate weld elbows, which are expensive material inputs to begin with. You eliminate the material waste from cutting those elbows and from fit-up issues. And critically, you eliminate the need for weld, grind, and finish operations.
Right. Think about a corner on a polished stainless handrail, welding two pieces together that requires so much time-intensive grinding and polishing to hide that seam.
And if you bend it perfectly in one piece, that labor is just gone.
Can you give us a tangible comparative example? What kind of time difference are we really looking at here?
Okay, so if a traditional fabricator needed to create a 90-degree corner on a stainless pipe using cut and weld methods, they might spend, 15 to 45 minutes on fit-up, tacking, welding, and then extensive finishing to make it look seamless.
And with the Ercolina.
With the Ercolina mandrel bender, once that program is loaded, you produce that perfect 90-degree corner in seconds. With a superior, clean structural bend, the labor cost reduction is immediate and it's ongoing.
The source material really highlights this with the Handrail Professional Series package. That looked like a perfect turnkey solution designed to get you straight into profitable work.
It's a phenomenal case study. The package gives you the AB 3-axis CNC machine, but critically, it bundles in the specific expensive tooling sets you need for high-demand applications, like 1 1/4 inch and 1 1/2 inch Schedule 40 pipe.
So it's ready to go out of the box.
It's ready to go. It also includes the auto mandrel lubrication pump, support software like BendTech for generating data, and importantly, factory machine training.
Ah, factory training. That addresses one of the major questions we always have about high-end CNC equipment, the learning curve.
Exactly. An investment in a system this complex has to be supported by training to realize its full economic potential. And the result of this turnkey system is stated as the ability to produce handrail to design in minutes.
In minutes.
That kind of throughput is achieved because the tool sets and their specific data files, like the proper machine start position, are stored. So the operator can switch rapidly between jobs and material sizes without extensive manual calibration.
And if an engineering firm uses external software, they can just use the optional BendTech or the direct import software for IGES, Tekla, and DXF files.
And that's the final step in optimization. It completely integrates the design office with the shop floor. By importing a Tekla or DXF file, they bypass data entry errors, they maximize repeatability, and they ensure that the finished product precisely matches the engineer's intentions.
All while eliminating hours of fabrication labor.
That's the bottom line.
This deep dive has really illustrated the technological shift driven by systems like the Ercolina ErcoBender. We're moving from the variability of manual manipulation to this highly sophisticated, automated, software-driven fabrication. The machine's sheer strength allows it to handle materials up to 3-inch tube and 2-inch Schedule 40 pipe, but its real value is in the precision it maintains.
And that precision is rooted entirely in that control system. You have the Y-axis for feeding and the B-axis for rotation, handled by highly accurate electric servos, and they're perfectly synchronized with that powerful hydraulic CNC C-axis for bending.
And for fabricators, the breakthrough moment really is that ability to program out material springback for every single bend angle.
Guaranteeing perfect, high-quality results, instantly and repeatably.
The economic case is undeniable. You've got reduced labor costs, the elimination of costly, time-consuming welding and grinding, and just improved quality delivered at scale.
Absolutely. And this leads us to a final thought for you to consider. This technology offers unlimited program storage and quick importation of these highly complex engineering files, like IGES and DXF.
So,
If the manufacturing floor can instantly and flawlessly execute bend programs with this level of, half a degree stability, how does the removal of previous fabrication constraints, like the difficulty of complex geometry or the cost of error, how does that fundamentally change the design complexity that engineers can now afford to tackle?
the machine doesn't just execute the design, it's actually pushing the envelope of what's physically possible to design in the first place.